Now it's time to get out of the office, and we're going to join a trip recently that we took out of Oceanside in San Diego to do some underway CTD testing, and so this video should give you a good idea of the deployment and recovery procedures. The underway CTD is installed on the rail here. The tail spool is in the rewinder. We've just loaded about 400 meters of line onto the tail spool, and now we're ready to connect it to the probe so we can do our first drop. You can see that the winch is installed on the rail close to the center line of the boat, which is ideal. We always recommend the winches mounted as close to the center line as possible. Also, we recommend that it's mounted as far aft as possible, so the arm extends as far as possible over the back rail of the ship, and that's simply to keep the probe away from the ship when you're recovering the probe in the final stages. So if it swings around, there's less likelihood of it hitting the ship and becoming damaged. Remember, especially for the CTD, that the conductivity cell is glass, so it's quite fragile and should be fine under normal conditions, just with the normal deployment and handling. But if it has a sharp impact against a steel-hulled ship, there is a high likelihood that the conductivity cell can become cracked, and so then there'll be problems with the salinity data from then on. So always we need to be careful where the winch is installed to minimize the potential for the probe to hit the ship. Because of the fragile nature of the conductivity cell in the CTD probe, we developed a foam bumper that can be slid down the line during final stages of recovery, and you should always use this, even if it's fairly calm and probe recovery looks fairly straightforward. It's always best to be safe. Slide the probe bumper down the line. What that will do is fully encase the probe during the final stages of recovery, so if it does swing around like a pendulum and it does hit the ship, then there won't be any damage. Maybe it take you a few extra seconds to slide the bumper on there, and it'll delay the recovery of the probe just a few seconds, but it'd certainly be worthwhile to make sure every time the probe's recovered safely, and there's not an expensive repair charge, and also your data quality will remain good. So always use the bumper. So something to consider when situating a winch on the ship is keeping it as close to the center as possible, and another benefit of doing that is the water velocity behind the boat at that point is the lowest relative to the ship. So if you look at the water on the port or starboard side, that's going past pretty much at the speed of the boat, obviously, but behind the boat, in the wake, the water really isn't moving at the same speed, and just behind the boat it's practically stationary. So that's always the best position to be deploying and recovering the probe, where the water really isn't moving. But if you do have to move the winch out towards the corners, which we often have to do, as sometimes the space is at a premium, so we have to move the winch into a non-ideal situation, which we can do. So on large vessels it really doesn't matter quite so much, but on a small boat like this, if you move the winch out too far to the corner, the controls may become difficult to access. So always need to remember that the controls are on the left side of the winch when the winch is in the deployment position, and so it's easier to move the winch to the port side, so the operator is always going to have a good view of the controls. The worst thing to have is the winch right out in the corner and the operator has to reach over to gain access to the controls without actually being able to see the controls, and that's a recipe for some challenges in operation if you can't see exactly what position everything is in. So always move the winch out to the port side if you do have to move it out. You see the yellow power supply box underneath the winch. Always make sure that's firmly secured. Needs to be fairly close by. The power leads from the power supply to the winch and the rewinder can only be at most 6 foot in length. The cables that are supplied with the system are the longest you can use without introducing problems in the winch or rewinder operation. So you cannot extend those 24 volt cables any longer. The power supply will run on 110 volts or 240 volts, and as I said, it outputs 24 volts to both the rewinder and the main winch. There's a power switch on the power supply that turns off the power to both the winch and the rewinder, and about 50 feet of mains cord is supplied with the system. One final point to make is the probe holder. Always make sure detergent is added to the water inside the probe holder, so the sensor, whether it be the sound velocity or the CTD, is well wet with detergent before the probe's deployed. It makes for better data in the top few meters of the water column if detergent is present in that. It provides a film on the sensor faces that allows them to become water wet much more quickly than if the probe was dry or was just stored in water without any detergent added. Okay, so now we move on to show the actual deployment. So first, the TOS ball with about 400 meters of line is taken off the rewinder and attached to the probe. Fairly quick and easy to do that with the special coupling that we use. Make sure it's nice and tight and firm when you put that on. And then the winch is rotated to the deployment position. Again, it's fairly easy to do this with the probe nice and close to the winch. Check the level wind goalposts are down. They can interfere with the line being paid out. So we'll show that again. Different deployment. Maybe we'll be going a little bit faster this time. So we'll take the TOS ball off, attach it to the probe. Now's a good time when you've finished coupling everything together to check that all the screws are tight, the line's in good condition, nothing is out of the ordinary with the probe. We recommend always being vigilant, making sure nothing comes loose. The probe gets a lot of vibration when it's being recovered, so there's several screws in the probe there that you need to check on a pretty regular basis. So take the magnetic plug out, and the probe logging has commenced. It's important to drop the probe from the vertical. Don't throw it overboard. Drop it nice and gently. Start the timing so you've got a good idea of the probe position through the drop. So we'll take another look at that drop. And this time, have a look at the line as it comes off the winch. You'll see there really isn't very much tension on it. All the winch is doing is paying out line to account for the motion of the ship. Remember, as the probe drops, the line is paid out from the tail spool, so the probe isn't pulling any line off the winch. It's really only the drag of the line in the water that's pulling the line off the winch itself. As the vessel moves away from the drop point, more line is in the water, the drag on the line becomes greater, so the tension in the line will be greater. But still, it's not the probe pulling the line off the winch, it's the movement of the ship away from the drop point that's pulling that line off. This last deployment video shows the CTD probe being deployed using the Series 1 winch system. So the magnetic plug is pulled to start the probe logging. Probe is going to be dropped gently into the water right behind the ship, that really hardly moving relative to the vessel there. You get a good indication of the relative velocity. You'll see the line as it's paying out. Again, not too much tension on the line there. Get quite a nice indication of how the line pays off the winch. It's really only being pulled off the winch there by the movement of the ship. Now we're back to the Series 2 system showing the line being paid out. We have about 1400 meters of 500 pound line on this particular system. If it was configured with 300 pound line, we could get up to about 2000 meters of line on the winch. That would be for slower, deep profiling. At the base of the winch spool there's 150 meters or so of red line. You should never pay out the red line. When the red line becomes visible on the spool, stop the winch immediately. The CTD probe drops at about 3.5 meters per second. With 500 pound line we can load up to 600 meters of line on the tail spool, which means that for a drop time of 170 seconds we can achieve 600 meters. If instead of 500 pound line we had 300 pound line, which we use for profiling where the vessel is moving slowly or even maybe stationary, we can get up to 1000 meters of line on the tail spool. So that means at a 3.5 meter per second drop speed over 1000 meters, the drop time is 285 seconds. So for both of those situations, 170 seconds for 500 pound line and 285 seconds for 300 pound line, there is no more line left on the tail spool, and so the probe, as it continues to drop, will pull line off the winch only. And because of the several hundred meters or even more than 1000 meters of line out in the water, the probe has to pull all that line down with it, and there's quite a lot of drag on all that line, so the probe immediately slows down significantly when all the line has been used up from the tail spool. So it will decrease from 3.5 meters per second immediately to 1.5 or 1 or even less than 1 meter per second, depending on the amount of line out. So there'll be a sharp break in the drop speed when all the line is used up from the tail spool. So the best way to get deep profiles is to make sure you wind the maximum amount of line onto the tail spool every time, because for every second of drop time with line spooling off the tail, you're going to get 3.5 meters of depth, whereas if there's no line on the tail spool, just pulling line off the winch, you're only going to get maybe a meter of depth for every second that you use. To clarify that point, the 1 meter per second drop speed applies to the period after the line has been spooling off the tail. Maybe the probe is at 400 meters, 500 meters or 600 meters, and then subsequent to that, when all the line has been used up from the tail spool, then it will start dropping at the reduced rate of 1 meter per second. If it's down at 600 meters, maybe it's only half a meter per second. If the cast is shallower and we're only talking about maybe 300 or 400 meters, then we would expect a meter to a meter and a half per second in drop speed afterwards. It really just depends how much line is out and how much line the probe needs to drag through the water. And obviously the deeper the probe is, the more line it has to drag through the water, so the slower it will descend. So the descent rate of the probe with no line on the tail spool just gets lower and lower as the probe gets deeper and deeper. So far all the deployments we've shown have line on the tail spool. This time we've got a winch only, no rewinder, and this probe is being deployed in tow-yaw mode with no line on the tail spool. This is a sound velocity probe. Quite often the sound velocity probe is used in this fashion. It drops quickly, so you can achieve typical survey speeds up to about 8 knots, 400 meters without even rewinding. So it makes it a simple way to deploy the probe. You can see a close-up of the controls that are used whilst deploying the probe. So drop the level 1 goalposts and apply the brake, and then the clutch can be put in the off position to allow free spooling, and the probe can be released. So when the designated time has elapsed, the brake is applied, and then the clutch moves to the full position to lock the spool. Then you can let go of the brake, turn the level wind on, and then you can turn the winch motor onto fast to recover the probe. When the probe's close to the ship, again move on to the slow setting to recover the probe carefully close by. When doing toyo profiles, as you haven't got any line on the tail spool, you can lower the probe down closer to the water before you drop it. And it's sometimes a good idea to lower the probe down close to the water and drop it from there. You can get a nice repeatable drop rate, especially if you're doing very shallow profiles. And this particular video has the CTD probe with floats on the tail spool, and those floats are added when working in shallow water to slow the descent rate down from about 3 meters per second to 1.5 meters per second. The tail spool can be disassembled and the floats slid on. Now we'll review some charts that explain the probe drop rates in a little more detail. So now if you look at this chart, it will explain the differences in drop speed in the different parts of the descent. So the chart shows the CTD drop speed in meters per second on the x-axis versus the depth. So this is one complete downcast to about 580 meters. So the green box is showing you the 500 meter portion of the cast where the line is spooling off the tail spool. So 500 meters of line was wound onto the tail spool. The probe drops on the average about 3.7 meters per second, so a little bit higher than the 3.5 conservative estimate, until all of the 500 meters of line have been paid off the tail spool. And you'll see at about 510 meters the drop speed reduces from 2.5 to 3.5 meters per second when the line is spooling off the tail, down to about 0.6 meters per second. And that sharp break in speed is when all the line is paid off the tail spool, and now the probe is simply pulling line through the water, eventually off the winch. So we have at least 510 meters of line that needs to be pulled down through the water, plus all the line that's been paid out on the surface. So that's a lot of line that the probe needs to pull down, which explains the large decrease in the drop speed. You'll notice below about 400 meters in the profile, the drop speed changes between 2.5 and 3.5 meters per second in a repeating pattern, and that is fairly common, and it's a result of the line paying off more quickly in one direction than the other. You'll remember that the rewinder loads line onto the tail spool in two directions, so it either pulls off with the line being unwound in the direction of the probe's fall, or it pulls off in the opposite direction. And what we find is when the line is pulling off in the opposite direction, there's less resistance to the probe's descent, and so the descent rate is faster. So as the line is pulled off from one end to the other, the drop rate changes, as you can see on that chart. The current CTD and SV software allows instantaneous plotting of the probe drop rates when the data is downloaded, and the reason for that is the drop speed is quite an important parameter to keep an eye on. What you need to do is make sure that the variation in drop rate doesn't increase much more than you see on the chart here. Certainly the lowest drop speed with line on the tail spool shouldn't be much less than about 2 meters per second. The reason why it's important to keep an eye on the drop speed, and especially the change in drop speed as the probe gets deeper, is that it's a good indication of the efficiency of the rewinding process. The amount of the drop speed variation is dependent on the tension on the line during rewinding. So good profiles with the right tension on the line during rewinding, and that's about 4.5 pounds, will have a smaller variation in the drop rate, especially at the deeper part of the profile. If the rewinding is performed with inadequate tension, which we describe as a loose wind, the worst case being the operator forgets to put the clutch in the slip setting, then the variation in drop speed will be larger. The reason a loose wind promotes this large change in the drop speed is the layers of line on the tail spool, if they're not wound on with enough tension, can start to interfere with each other. So the outer layer of line, instead of being a discrete layer on top of the layer below, the two layers merge together. So the interference between the two layers will cause the line that's paying off the probe to be pinched and reduce the speed at which the line can be pulled off. So as explained earlier, the line will pay off the tail spool a little bit faster in one direction than the other, but the loose wind condition just makes that situation much more noticeable. Now you may be wondering what the probe drop speed is with no line wound onto the tail spool. That is, the probe's dropped from the surface with no rewinding stage in a TOS mode. We'd actually recommend the TOS mode be used for all profiling to depths shallower than about 250 meters for the CTD. You'll be able to accomplish a profile in a shorter time, omitting the rewinding step for profiles in the upper 250 or so meters. So you can see from the chart, when the probe is first dropped, it drops at about 3 meters per second for the first 100 meters, and as it's dragging all the line down with it, the drag on that line increases as more line is paid out, and the probe descent rate slows. So by about 400 meters of the profile, the probe descent rate slowed to just over 1 meter per second. And so this gives a good indication of the drop speed you will get for a TOS cast down to about 400 meters. So when planning profiling, the different drop speeds can be used to determine what's going to be the fastest way to get the profiles you need. In comparison to the CTD, the sound velocity probe has a faster descent rate. Instead of 3.5 to 4 meters per second whilst descending with line spooling off the tail spool, the sound velocity probe under those circumstances will drop at about 5 to 5.5 meters per second. Similarly, in TOS mode with no line on the tail spool, the sound velocity probe is going to drop up to about 1 meter per second faster than the CTD probe. Now we're going to go back to the video and look at the recovery stage when we've completed the downcast. First the brakes applied, and then the clutch is moved to the full position which locks the spool, then the brake can be released. The level wind's then turned on and the goalpost flipped up, and then the winch motor can be put into fast to recover the probe. One trick you can use is to pull out the pin from the swivel base that allows the winch to rotate freely. Although it's okay to take the pin out and allow the winch to rotate freely, what you can't do is lock the winch in position at the wrong angle. Here you can see a situation where the winch arm is at 90 degrees to the probe recovery direction. And the problem with this is the pin that locks the swivel base is not strong enough to handle the load if the winch is set up in this arrangement. If you can imagine, all the pull on the end of the line is pulling the block and trying to rotate the winch. And so if you can imagine the situation without the rope holding the arm, the only thing that is preventing the winch rotating to point directly aft is the pin that's locked in the swivel base. And that pin can't handle the forces that are generated, so the end will shear off. So the way to avoid snapping the pin is to ensure that the pin is not taking the force of the pull of the probe trying to rotate the winch. And the best way to do that is fairly simple. Tie a rope around the arm and attach it to the ship structure like shown here. It needs to be nice and tight so the rope is taking the force of the probe recovery and not the swivel pin. We recommend that you only use the system in this manner if you absolutely have to. It's always best to have the winch pointing directly aft when you're recovering the probe. So now to the probe recovery. Probe's just about at the surface, difficult to see, but it's a few hundred meters behind the boat. The line is tight and entirely clear of the water right the way back to the probe. Sometimes people imagine the line is submerged when the probe's being recovered, but as we're underway, the tension on the line from the probe in the water is quite substantial, so that keeps the line taut and clear of the water. So it's useful if there's towed equipment behind the boat, so when the probe is being recovered, it can be recovered on the surface above anything that's towed behind the boat. As the probe gets closer to the boat, you just need to be vigilant, be ready with the slow switch to slow the probe recovery down so you can get the probe back safely. As the probe gets closer to the boat, you'll see that the recovery speed is pretty fast, so if you're not ready on the switch, you potentially could have a problem trying to pull the probe through the block. So always better to be safe than sorry and slow the probe down early on in the recovery. This video actually shows the probe recovered pretty quickly, so maybe this is a little bit too fast at the final stages, but always be careful when recovering the probe here. Now we have another recovery, and this shows quite nicely why it's good to have the winch in the position in the middle of the boat. You can see the velocity of the water fairly low where the probe is being recovered, so it makes it easy to handle the probe as it's coming out of the water. You can also see the pendulum effect occurring there, so all it takes is one big impact of that probe onto the boat, and there could be a problem with the conductivity cell. So you need to be very careful when recovering the probe. So now we're resetting the system for the next cast, so the probe tail spool can be removed, data can be downloaded if necessary, and the probe tail spool can be put back on the rewinder to load line for the next cast. So here's a final probe recovery to give you another idea of what the probe looks like as it's being recovered. Sometimes it will bounce around on the surface, sometimes it may even disappear just under the surface for a little while. It's always a little bit of fun and games as the probe is pulled closer to the ship, especially if you're going 8, 10, 12 knots. Careful use of the slow winch setting to make sure the probe's recovered nice and safely. So now this is the time where there's the most danger for any probe impact, especially if you're not using the probe bumper, which we would certainly recommend that you use that, but having an assistant would help, just to make sure you can keep the probe away from the hard surfaces of the boat that you're working on. So when the magnetic plug is put back into the probe, then that will activate the Bluetooth antenna on the CTD for 2 minutes, so you can then download the data if you wish. Okay, so I said that will be the last recovery video. Well, that's not quite true, because we have one more here, and this is showing you what the recovery looks like at 3 knots. The big difference is the probe surface is much closer to the boat at 3 knots. So here you have about 50 meters between the probe surfacing and the boat. So you need to be more careful the slower you're going to watch for the probe as it surfaces. So here we have a video sent in by one of our customers, and although it's a bit of an extreme example of the underway CTD in action, it does show some important points for installation and use of the system. See the long pole they have there? That's to help them recover the probe without it hitting the ship, especially in the extreme conditions they're working in. The system's mounted on a post right in the center of the vessel, which is an excellent location under the A-frame. They're lucky they were able to get that prime spot there. It's right at the rail, so the arm is extending nicely over the back. It's a good post mount, very secure with the power supply underneath. On this cruise they were profiling to about 500 meters using the 500-pound line set up, so fairly typical. And of course at this point, with these sort of conditions, this was the only CTD they could get over the side, so it's quite useful for getting data in difficult conditions where you just can't use the big CTD rosette. So they were very careful to make sure the probe was recovered safely, and this is really the key part of the whole operation here. You know, just one slip and it hits the ship, and your conductivity cell can become damaged, and that's the end of your salinity data from then on. So good system they got working here to get the probe back safely. Thank you for watching this training video. Make sure you take a look at the other videos in the series that explain the rewinding process in detail. That's really a key part of the operation of the underway CTD and the underway SV systems.